commutated devices. Commutation means it is the turn-off process. So the turn-off process will be self turn-off process in the devices like a GTO, gate turn-off transistor, IGBT, insulated gate bipolar transistor, and MOSFET we will use for the medium power applications. MOSFET we will be using, and BJT also, that is power BJT, power transistor is also used for the inverters. Preferably for high power applications, we will go for the IGBTs. And the normal inverters will be line commutated inverters and source commutated inverters. The line commutated inverters means, so that will be a classification of phase control rectifiers that we have studied in the second unit, that is a line commutated inverter. There is a phase controlled rectifier. If we are increasing the firing angle above the alpha is equal to 90 degree, above 90 degree means, so that will act as a line commutated inverter. So that will not be a practical inverter. So that is a classification of the rectifier, phase control rectifiers. If the firing angle is greater than 90 degrees, it will act as inverter. So that is called line commutated inverter. The next one, force commutated inverter is also there. That means for DC supply, we have to turn off the devices which we are using for the inverters. So the inverters will have some powertronic devices. To turn off that devices, we have to apply some external components for the turning of the devices. So that is called force commutated devices. If you are going with the SCR means, we have to go for the force commutated inverters. And the main classifications of inverters are a voltage source inverter and current source inverters. So the voltage source inverter means the input you can shift voltage source. The output voltage is also a constant AC output, but depending upon the load, the current waveforms or the nature of the current will be varying. So that is called voltage source inverters. The output voltage will be a constant voltage, and the output current will be variable. But in current source inverters, it will be the inverse of the voltage source inverters. The output current is a constant parameter, and depending upon the load, the output voltage nature will vary. So in both the cases, what will be the source means, in a voltage source inverters, the input will be a constant voltage source, and in current source inverters, the input will be a constant current source. So that is the difference between voltage source and current source inverters. And the applications means, so these inverters will have the variable voltage and variable frequency, so that we can, mainly it is used for the speed control of the AC motors. So that is called as adjustable speed AC drives. So for controlling the AC motors, we are going for the inverters. And induction heating, then standby aircraft power supplies, UPS, that is uninterrupted power supplies for computers, HVDC transmission lines, and static VR compensators. So these are the applications of the inverters. And the next one is what is meant by voltage source inverters. So here it is the picture that is representing the VSI, voltage source inverter. So already I said the voltage source inverter is a constant input voltage source. So here we are having a three-phase AC supply that is converting that AC into DC by means of uncontrolled rectifier. So uncontrolled rectifier means it is a three-phase diode rectifier. So diode rectifier is called as uncontrolled rectifier. So that will convert that AC into DC. So for maintaining the constant voltage, we are connecting an capacitance. So this capacitance will give constant DC input voltage to this inverter, so that it is called, we are calling it as voltage source inverters. From this DC capacitor, we are obtaining the constant DC. So the link which is connecting this rectifier and the inverter is called as DC link, and so that it is called as DC link capacitor. And this capacitor is large and can be considered as an ideal voltage source. So since it is a high voltage source, it cannot be short circuited. So it is a direct short circuit of the input. So it cannot be short circuited. So that from the constant voltage source, that is capacitance, it is giving us input to the inverter, and the inverter will convert that DC into AC depending upon the load requirements, depending upon the voltage and frequency, what is the requirement of the load. So this inverter will convert that DC into variable AC. So here the capacitor will play the major role. So that is giving major constant input to the inverter. So this will be of higher value when compared to the inductance. And the next one will be current source inverters. So here we are not having that capacitor, since here the input of the inverter is a constant current source. So for a constant current source, we are connecting a large inductance in the DC link. So here also we are having a three-phase uncontrolled rectifier that will be convert AC to DC, and this is the DC link. In this DC link, we are having a large inductance. So the inductance property, what is the main property of the inductance means? So that will not allow the sudden change in current. So that will not allow the sudden change in current, so that it will provide constant input current to the inverters. So here it is mentioned that the inductor is large and can be considered as an ideal current source, and this will give the constant current input. So it cannot be open circuited. Normally, the current sources will not be open circuited, and the voltage sources should not be short circuited. So here the inductor is a current source, so it should not be an open circuited. So that will give the constant current input to this inverter, and the output will also be a current. That is, output current will be a constant parameter, and we depending upon the load, either it may be a resistive load or inductive load or capacitive load, the voltage nature will be varying. So both are in different manner. So here we are speaking about the output voltage. So in current source inverter, we are speaking about the current. So these are the main classifications: voltage source and current source inverters. Then next one, it is the single phase full bridge inverter. So it can be classified as half bridge inverters, full bridge inverters. So here, first we can see, for example, we can see the single phase full bridge inverter. So this is the input DC source, and this is the load. This across this load, we are measuring the output voltage V naught. So we will get the output voltage as AC. So by means of using these four switches, we are having four switches: S1, S2, S3, and S4. By proper turning on, turning off these switches, we can obtain the AC across this load. So VDC is your input voltage, and V0 is your output voltage. So this VDC is converted into AC by means of turning off this and turning on and turning off process of these four devices. So here we are having the possible combinations of the turning on and turning off the switches. So if first one, if S1 and S2 is turned on, we will get the positive off cycle. So here mentioned, we are mentioning it as a single throw switch. So it can be any of the power electronic devices. It can be an IGBT, or for medium power applications, it can be a MOSFET. So for simplification, we are mentioning it as a single throw switch. So for first combination, we can turn on either any of the two switches. So for first case, we are taking it as S1 and S2. So first one, S1 and S2 is closed. So the current will flow from the positive of the VDC to S1, then to V0, and then it will return through the S2 to the minus of the VDC. So that will be considered as the positive direction or the positive voltage. So here we will obtain the positive cycle. The next combination is S3 and S4. So S3 and S4, we are closing the switch, and during that time S1 and S2 are open. So the current will flow in the reverse direction. So the current will flow to the S3 and to the right hand side terminal of the V0, and then to the left hand side terminal, and the current will flow in opposite direction to that of the previous case. So here it will return through the S4 to the minus terminal of VDC. So in previous case, it will be in left hand side to right hand side current direction, and in this case, second case, S3 and S4 is turned on, the current will flow from right hand side to the left hand side direction, that is an opposite direction. So we will get the negative half cycle output. So in during the turning on process of S3 and S4, we will get negative half cycle. When S1 and S2 are turned on, we will get the positive half cycle. And these are the possible combinations. The diagonally opposite devices will conduct, so that will have one positive half cycle and another one negative half cycle. Suppose we are turning on the devices S1 and S3 means, so there will not be any current flow, since the positive only is connected to the source and negative there is no connection. So the output voltage is zero. And S2, if S4 are connected also means, the negative only is connected to the load, so that we are not getting any output voltage. So V0 is equal to zero. So these are the fruitful combinations, that is S1, S2, positive VDC, that is positive half cycle, and S3 and S4 is negative half cycle. Suppose we can turn on the S1 and S4. So what will happen means, so that will be the direct for the short circuit of the input source. Likewise, S3 and S2 are turned on means, so like in that condition also the input will be directly short circuited. So that is not a preferable combination. S1 S4. This is called as leg. So the same leg devices will not be turned on for any circumstances. So that will lead to direct short circuit of your input voltage source. So here it is explained. So if S1 and S2 are turned on, so the current will flow like this. So that will give positive up cycle. And S3 and S4 will turn on, will be the current flow will be like this in opposite direction. And it is S3, the state 3 and 4. Here S1 and S3 are turned on. So the voltage will be 0. So here S4 and S2 are turned on. The output voltage is also again 0. And what will be the output we are getting as the across the load. Suppose we are having the DC input. If we turn on these switches, we will get the output voltage like this. So this yellow color indication, that is a square waveform, is your output voltage. So this is the maximum voltage. The maximum voltage will be equal to the input voltage source magnitude. Suppose we are having the VDC as 100 volt means, so in output voltage we are having this, the maximum value as 100 volts, and in negative half cycle also we will having the minus 100 volts. So we will get the square waveform or rectangular waveform as your output. So that is also an AC. Alternating current means that will have the alternating positive and negative supply. So here we are having positive and negative half cycle in the form of square waveform. But we have to obtain pure sine waveform as the output. So we have to calculate, or we have to extract the sine waveform in the output voltage waveform. So how we are extracting this output waveform as pure sinusoidal means, so in domestic applications in houses also you can see the inverters as pure sinusoidal inverters. So pure sinusoidal inverter will give the output voltage in the sinusoidal nature, but practical cases in all the inverters we will obtain only the square waveforms or rectangular waveforms as your output. So that is the impure form of AC. So according to Fourier series, when we are analyzing means that square waveform will comprises one pure sine waveform. In addition to that, we will having some additional extra frequency component. So that will leads to the distorted nature of the output. Suppose we are extracting the pure sinusoidal waveform means the remaining terms will be the multiples of that frequency. So what is the supply frequency of standard supply frequency of the supply means 50 hertz. So this green color waveform, that is fundamental, it is represented as fundamental first harmonic means. So that will be the 50 hertz waveform. That is the requirement of our load. But in addition to that, we will be having some third harmonic and fifth harmonic. So the first harmonic will have the frequency as 50 hertz. So the third harmonic will be having the frequency as 3 into 50, that is 150 hertz. So obviously fifth harmonic will be 5 into 50, that is 250 hertz. So, so this will be completing one cycle, that is 50 hertz. So before this, the third harmonic will be completing its three cycles. So it can be considered as third harmonic or 150 hertz output. And in addition to that, fifth harmonic will also be generated. So it will complete five cycles before the completion of single 50 hertz supply. So you can see this green waveform is one cycle. And before that, the brown color waveform, that is third harmonic, will completing its three cycles. And this gray waveform, that is the fifth harmonic, will be completing its five cycles before the closing of this single cycle. So if the sinusoidal plus third harmonic, fifth harmonics, and it has up to nth harmonic. So you can 3, 5, 7, 11, and up to nth harmonic we will be having. So we have to extract only this sinusoidal waveform as the output. So the remaining things are unwanted. That is the third, fifth, and up to nth harmonic that has to be filtered out. So if all these added means, so that will be the square waveform, and from that we have to obtain only the sine waveform. So if we are giving the same output, that is a square waveform as the output, so directly any electrical equipment, suppose we are giving this square waveform to the input to the any single phase induction motor or any type of AC motor, instead of giving the sine AC supply means, So what will be the disadvantages means? So that will overheat the motor. So instead of giving the pure sinusoidal AC supply, if you are giving the square waveform means, so we are having the harmonics in addition to that sinusoidal. So that will create unnecessary task ripple, and that will lead to heating of the motor. So that we have to filter out these harmonics, and we have to obtain only the fundamental alone, that is the 50 hertz supply. And in this diagram we can see, so this is the inverter output voltage, so that will be of pi and 2 pi, this will be of 50 hertz. And the second will be the fundamental component, that is the required one, that is of 50 hertz pure sinusoidal waveform. And this is the third harmonic, that is the so 150 hertz waveform, and fifth harmonic is 250 hertz waveform. If we add all these waveforms, we will get the square waveform. And if we filter out these harmonics means, we will get the pure sinusoidal waveform of only 50 hertz. And this is the block diagram. That is the basic block diagram for the inverters, how we are using or how we are obtaining the pure sinusoidal waveform for the load. So this is a DC supply. So it is given to the inverter that will give the square wave as the output. So we can filter out that harmonic so that the square waveform is converted into pure AC sine waveform. That is your 50 hertz waveform, and this 50 hertz waveform is given to the load. And first thing we can see what is the basic full bridge single phase full bridge inverters. So here we are having the four ACRs, T1, T2, T3, and T4. So already I have shown with the four switches, that is the SPST switches. So here it is replaced by an four ACRs. So that is T1, T2, T3, and T4. And across that each ACR we are having the anti-parallel diodes. The anti-parallel diode means both will be in oppositely connected. So the current flow will be in downward direction through this ACR, and the current direction will be in upward direction in through this diode. So both the current directions are opposite, so that it is anti-parallel connection. So here the four switches, the SPST switches in the first diagram. So here I have shown the diagram with the four switches. So these four switches are replaced by four SCRs in anti-parallel connection with four diodes. So here also, what will be devices which will be conducting for positive half cycle means the T1, T2 for positive half cycle, and T3 and T4 for negative half cycle. So here we are giving the gate pulses IG1 and IG2 for T1 and T2 for positive half cycle. So as long as you are giving the pulses to the positive conducting ACR, that is T1 and T2, so that will be in turn on condition. And after that, we are turning on the devices T3 and T4. So after that, it will be turned off. The gate pulses are removed and the SCRs are turned off externally. So after that, we are turning on the devices T3 and T4. The negative pulses are applied to T3 and T4, that is IG3 and IG4. So for this period, the devices will be conducting is T1 and T2, and the current direction will be from positive of Vs to T1A and to B, and through the T2 it will return to the negative of the Vs. So during this condition, the current will flow from A to B. So it will be the positive half cycle. That is Vs will be in positive, that is V0 will be in positive half cycle with the maximum magnitude of Vs. And during the conduction period of T3 and T4, the current direction will be, it is from positive of Vs, then current will flow to T3 and it will flow from B to A, and it will return to T4 and to the minus of Vs. So the current direction will be in opposite direction, that is B to A. Previous case it is from A to B, that is positive half cycle. Now it is from B to A, that is negative half cycle of the output voltage. So here also the maximum voltage will be minus Vs. So this plus Vs and minus Vs are decided by the input voltage magnitude. So this is for the resistive load. So for the resistive load, the voltage and current direction will be same. So here we can have the positive half cycle and negative half cycle. The current waveform nature is also a square waveform, and this is also the same diagram. And this is the half bridge inverter. So here we are having the two switches. So here we are having four switches, two switches for each half cycle. That is here we are having transistors. That is TR1 and TR2 for positive half cycle, 3 and 4 for the negative half cycle. And here this is a half bridge inverter means we will be having one switch for each half cycle. but the voltage input voltage source is divided into two separate sources. So here we are having the single input voltage source. So here we are having divided by two. That is it is a Vs, which is 100 means we have to separate it as Vs by 2 and Vs by 2. So here also TR1 will be conducting for the positive half cycle and TR2 will be conducting for the negative half cycle. So when TR1 is turned on, the current will flow in this direction. That is from the I0 direction is given, that is positive to minus negative is the positive half cycle direction. In negative half cycle direction, the current flow will be when CR2 is turned on, the current flow will be in this, that is left hand side to right hand side, so that for each half cycle the device is conducting a one, that is here TR1 for positive and TR2 for negative half cycle. So this will be for the resistive load. So in next class we can see the inductive loads and capacitive loads. So for this next class we can see. So the basic thing in inverters is, in a normal inverters are voltage source and current source inverters, depending upon the output waveform nature. Either it is a constant output voltage, it is a voltage source inverter, and either it is a constant output current, it is a current source inverters. And after that, we are having half bridge inverters and full bridge inverters. Full bridge inverters will have the two devices will be conducting for each half cycle, so that the device's rating will be less. And in half-bridge inverters, a single device will conduct for a single half cycle, so that the device rating will be high. And preferably, we will go for the full bridge inverters. And in resistive loads, the current and voltage waveforms are in phase. So in normal inverters, we will get the square waveform as the output, and we have to filter out to get the pure sinusoidal output waveform, and the remaining harmonics has to be filtered for the smooth operation of any electrical equipment, right? ஸோ இன்னைக்கு இது வரைக்கும் பார்த்துக்கலாம்ப்பா. ஸோ நெக்ஸ்ட் கிளாஸ் we can go for the inverters with inductive loads and capacitive loads. சரியா? ஸோ இதில் எதுவும் உனக்கு